Something I find a lot of my students really struggle with in their GAMSAT preparation are those organic chemistry reaction questions. And whilst I agree that they look really scary, if you have a solid grasp of the fundamentals, then they're really actually quite simple. So what I wanted to go through today was just kind of a crash course in organic chemistry. So how to identify functional groups, how to name compounds, how to draw compounds, just all of those really essential skills that you need for chemistry, and hopefully that'll help you out. Hi everyone, my name's James. I'm a first year medical student and I've been tutoring Section 3 of the GAMSAT for a few years now and have got a lot of good feedback on how I approach questions, so thought why not make a few videos to share and hopefully help some of you out. And if you do find the videos helpful, I'd really appreciate it if you could like, comment and subscribe. Okay, so let's get started with how to interpret chemical formulas and draw out molecules. So I think ultimately it's good to not lose sight of what we're trying to do. So what we're trying to do is see how the carbon are arranged and what they're bound to. So ultimately, on each of these things, you really want to be looking at the carbon and then trying to identify what they're bound to. Now, carbon can always bond four things. So if they're not bound to four things, it means there's an additional bond. And we'll go through that a little bit later. But what I want you to really remember is that carbon are always bound to four things. Hydrogen are always bound to one, so they're kind of a little bit easier. And it's just really about making these pieces fall into place. So if we look at the first one, we have these two carbon here, and we're just interested what's bound to that carbon. Now again, they're going to form four bonds, so each of them have to be bound to four things. And you can kind of see just by looking at it, even with that simple highlighter, that probably these hydrogen to the right of that carbon are going to be bound to that. There's three things that they're bound to. And it's kind of easy with the hydrogen because they can only bind to one thing, so they can't be bound to each other or anything like that. So they have to be bound to that carbon. So what this would look like, if we wanted to draw that out, is carbon bound to 3 hydrogen, and then carbon form 4 bonds, as I've said before. So that means we'll actually bind to this other carbon over here, and then that has its own 3 hydrogen there like that. I wrote it intentionally a bit of a different weird way as well. So I think ACER intentionally does this. They write things in different orders to get you a little bit out of your comfort zone. So just be really comfortable with all the different ways that things can be written. But essentially it's exactly the same. You're just looking for a pattern that describes how the things are bound to the carbon and how the carbon are bound to each other. So this is exactly the same molecule, it's just written in reverse. Okay, so if we move on to the next example, it looks a little bit scarier, but it's still the same kind of premise. So we want to look at these carbon and then try to determine what's bound to what and which carbons, if any, are bound to each other. So the first thing I think, if there's something looks a little bit scary, start with the simple first. So to me, it's quite clear, especially based on that first example, that these are going to be bound to that. These 3 hydrogen are going to be bound to those respective carbon. So if we just kind of ignore those for a little bit and just, write them out, we know that this is going to be the case on either side of the molecule. So that's a good place to start. And then we just have to focus on that COO in the middle. And if you kind of look at it, just even what's most directly adjacent to each of these carbon, it gives you a really good hint as to what's going on. So this has to be an O, and that's satisfied the 4 carbon bonding rule that we said before. And on the right hand side, it's bound to a carbon, and that again satisfies that carbon. So that's our 4 carbon. So those ones are all good. And then we just need to sort out this one in the middle. So it's got 1 bond here to the rightmost carbon, and there's 1 oxygen unaccounted for. Now, that can't be bound to either of the first carbons on the left or right because they're already full. So that means it has to be bound to this one. And if we just kind of put it somewhere in the vicinity, and then just think, okay, well, we need to tie all these things together. So we could try, maybe we try a single bond between these two. We think, okay, doesn't quite work, because if you look at this carbon here, so the problematic carbon in yellow, that's only forming two bonds, one with the carbon on the right and then one with the oxygen. And as I said, oxygen can only form two bonds, so that's not working for us. So we need to try something else. So maybe this is bound to that, that's our second bond to that oxygen. And then that's bound to that, which is 3. So we're nearly there. And then we're thinking, oh, okay, well, what's going on? Well, that oxygen can form two bonds, can't it? So there we go. So there's our fourth one. So it's all just, and that's what I was talking about. It's really important to know how many times things bind to each other, because that's going to determine the ultimate structure. So my advice is just start with the easy things on the left and right, or just whatever looks easy in the molecule. And then whatever's left, just a little bit of trial and error, and you'll figure out how the things are bound. If you just remember that rule that carbon bonds 4 times, oxygen binds twice, and hydrogen binds once. And kind of a similar example in this third one. So it looks very similar to the first example. So you can probably already start to tell that these are bound together and these are bound together, and they're attached by that carbon. So let's start drawing that out. So we've got C, hydrogen, hydrogen, carbon, hydrogen, hydrogen. And if you just have a look at that, these hydrogen have their single bond, so they're always good. But if we look at these carbon, they're each only forming 3 bonds. If we look at this one in red or something. So we know, just based on the chemical formula and how many bonds there are, that to satisfy both of those, there has to be a double bond in the middle. So that's why understanding the chemical formula is so important, because that will change the naming of the compound. It might change how it reacts. It might change there might be a stipulation in the stem that says these things don't react or something like that. So it's really important to know exactly what the compound is based on its formula. Okay, and I just want to stress as well that it is important to know all the different ways that they can be represented. So what we've been doing so far is called a semi-structural kind of formula, but you kind of have, it's broken into parts, but you can have all of the atoms present in a molecule kind of aggregated together. And that's what these two down the bottom are representing. So if you have these, it's just a little bit more trial and error, but just do the same kind of process. So if we have C3H8, well, we know that the hydrogen can't bond to anything other than the carbon, because they only form one bond. So these carbon have to be bound together. And then you can just fill in the hydrogen around the carbon, and you see that it's just like that. It's just kind of a simple saturated hydrocarbon. But you can have examples where the chemical formula actually tells you things about that molecule. So if we take the same thing, but all we've done is reduce the hydrogen count by 4. So here we have H4 compared to H8. You can see that this isn't going to add up. So you could just gradually add in a couple of hydrogen, let's say here and here. So that's 4 hydrogen. And then it's just a bit of trial and error to see if you can make that work bond-wise. So you can't bind to any more hydrogen because there is none, but remember you can form double bonds. So that would just be an indication about kind of what molecule you're forming. And again, that can be really important. So keep an eye out for those differences in formulas. Okay, so now we've gone through a little bit about the basics of how we draw out molecules. I'd like to go to how we actually name compounds. So to do that, the first thing you need to understand is the functional group. And what the functional group will do is provide the suffix, so the part on the end of the word that you call the molecule. So these are going to just take a little bit of rote learning, but I'll try to make them kind of as easy as possible to understand. So alkanes have the suffix ane, so that's nice. And all they are is just what are called saturated hydrocarbons. So that's just carbon that are bound to each other and all of their possible bonds are taken up with hydrogen. So if you look in the middle, that demonstrates it quite well. That's just 3 carbon that are bound together, and every possible other bond that those carbons can form is 2 hydrogen. And you can see it written a few ways. So you could see it in this semi-structural thing. You could see it written like this. I don't know the particular names for these things, but you can kind of see it completely broken up. Or you could see it as a line. So the line takes a little bit of explaining, but essentially each of these points is just a carbon atom. And you just need to kind of imagine that there are all these hydrogen bound to it, but you don't write the hydrogen out. Sometimes you might see it written with those in there as well, but that's just what the line diagram means. It's very common that you might just see lines. So you just need to know what each of those kind of points of the line mean. And then lastly, you could also just see it written as R. So if you see an R in any of your problems, that just means a hydrocarbon of any length. So this could be, just by seeing R, that doesn't mean anything. So if you have it drawn as a line, you can count the vertices and know how long the hydrocarbon is. If it's R, it could be anything. It could be 5 carbons, 100 carbons. You don't really know. All you know is that it's saturated with hydrogen. So you'll often see this R, and it just represents a variable group in that reaction. Moving on, we then have alkenes, and the suffix there is -ene, so that should be very easy to remember as well. And all that is different to an alkane is just that it has a double bond somewhere in it. We then have alkynes, and again, suffix -ine, so quite easy. And that's just a triple bond. So it kind of just progresses alkanes, alkenes, alkynes. And it's in alphabetical order, so that's maybe an easy way to remember them. And then next we have alcohols. So alcohols have the suffix -ol, and all they are is just a hydrocarbon with the additional OH group there at the end. I've also written it in the other form, so you might see it as ROH, and that just means a hydrocarbon of variable length with an OH group or a hydroxy group at the end. Moving on to some of the more advanced functional groups, something I find extremely helpful to remember is what I call the common backbone. So this is just R bound to a C, double bonded to an O, and then something else. So this is the backbone of all of these different groups. So if you can remember that R, C, double bond O, it'll get you halfway there because all you need to remember is one little part that goes on the end. So let's go through these. So now we've got an aldehyde. Again, the suffix should be quite easy, al, so it'll be something al. And how I remember aldehydes is that of these groups, and these are the most important ones that I think you remember, of these, they're the only one that has a H in their name. So how you do that is just hydrogen, a hydrogen at the end of the common backbone, and that's an aldehyde. We then have carboxylic acids. I don't have a good way to remember these, but for some reason I find it really easy to remember that OH. I don't know why, but if you remember the common backbone and then OH, it just seems to stick in a lot of people's minds. Then for the other ones, for ketone, we have an O in the middle, and what a ketone is an O in the middle of 2 hydrocarbons. So I find that's a good way to remember that one. And lastly is the ester. So I kind of think that ER is similar to OR. So that's what goes on the end here, is an O bound to another hydrocarbon group. So again, these are just going to take a little bit of memorization, but if you can get the common backbone, you're going to be more than halfway there to remembering it. Okay, so now that we know the functional groups, this is how we name our compounds. So the first thing you're going to do is identify the functional group, and that will give you the suffix. So for example, if it's an alcohol, the suffix will be ol, okay? Now every suffix needs a prefix, and how we do that is by counting the longest hydrocarbon chain, which contains the functional group. And how we determine the prefix is however many carbon are in that hydrocarbon chain tells us the prefix. So something that I use that makes it quite easy to remember is Mary eats plums before playing hockey. So I've written that out here. And that gives you a kind of indication of the actual name that's given to that carbon group. So for example, if you have a hydrocarbon of length 4, then that's going to be butyl. So if you identified the functional group as an alcohol and it was 4 carbons in the longest chain, then that will be butanol. And we'll go through some examples of this, but that should hopefully help you get the prefixes as well. And there are some additional steps. So there's numbering, and I'll go through that. That'll be far easier with the examples, so just don't worry about that one too much now. And then you have to account for everything else. So again, I'll do that with the examples, but essentially, if you have the longest chain, there might be extra parts hanging off that chain, which we need to include in the naming of our compound. And that will be using those prefixes again, but it'll make more sense when we do the examples on the next page. So here we go with some examples. So in the top right, I've just done a kind of truncated version of those rules that we went through. So step 1 is find the functional group. So if this is a little bit hard at the moment, don't worry. You will learn these functional groups, but just really make sure that you do, because I think it's essential. So with this first one, the functional group is just this OH here, which is an alcohol. So we know that our suffix is OL. I might actually just write it OL for now. Second thing we do is we count the longest carbon chain. And in this molecule, we only have 1 carbon chain. So we just go 1 carbon, 2 carbon, 3 carbon. This isn't a carbon at the end, that's the functional group. So our longest one is 3. Mary eats plums, which is propyl. So this is just propanol. And it's easy as that, just combining the prefix and the suffix. If we move down, we'll see that we have this thing, and it looks a little bit scary, but remember, any hydrocarbon is just an R. So this is essentially an R group. So if we highlight the R group, the C and the double bond O, hopefully you're seeing that common backbone. So the additional part that we have on there is the hydrogen. And if you remember the kind of thing that I use to remember it, is aldehydes are the only one with a H in their name. So if you've got just a hydrogen, then it's an aldehyde. So our suffix is al. And again, we're going to count the longest hydrocarbon chain. So 1, 2, 3, 4, including that carbon. So that will be Mary eats plums before butyl. So this becomes butanol. Now you might have noticed that I haven't really done the numbering or the everything else steps, and that's because these ones are quite straightforward. However, on this example, this is where the numbering is going to become important. So if we look, we have kind of 2 R chains. So this could be an R over here, but this one could also be an R group over here. So whichever way we look at it, we have our common backbone with the C double bond O. Let's just say we do that. So we know that, and then we can work out from that, well, we've got an O in between 2 hydrocarbon groups. So this is a ketone. So that has the suffix -one. And if we count, so now we can keep going through our steps. So we'll count the longest chain. So we've got 1, 2, 3, 4. So it's a butanone. But what we need to do is number the functional group on the lowest carbon, because if you see here, depending on which carbon we start from, we'll get a different carbon. So it's important to know where the functional group is in the molecule. So if we start this way, you can see that the functional group, which is this part here, is attached to the 3rd carbon. However, if we start our counting from the right-hand side, so 1, 2, 3, 4, now all of a sudden, the functional group is attached to the 2nd carbon. So it's very important. In this one, it doesn't matter as much, but in a lot of molecules, it will matter the numbering. So when how do you decide? Because it could be either of them. Well, the answer is you pick the direction which gives the functional group the lowest number. So in this case, we would actually count from the right-hand side, moving towards the left, and then we just put this at the front. So 2-butanone. So that's how numbering works. You basically just need to count the hydrocarbon chain, so exactly as we have done before, but just be aware that you might need to change it depending on the direction. In these first examples, it doesn't. Why it doesn't matter is because we would actually count from this side, and this would become 1 propanol. And that doesn't, if we have a 1, we just leave that out. So that's why the numbering doesn't really matter in those first examples, but we are still doing it there because this could be 1 or 3 propanol, but you obviously minimize the number, so you have it as number 1. So when you got that simple chain, it just becomes the first carbon. Okay, so moving on, we've got this one. So first thing we do is identify the functional group. And what I can see here is a double bond in there. So that would be an alkene. So now we need to count the longest hydrocarbon chain, and take your time doing this. Just make sure you count the longest, you definitely count the longest chain. But I would probably think that this is longest. So that's 6. So Mary eats plums before playing hockey. So this is hex. And our functional group is an ene or an alkene, so our suffix is ene. So this is hexene. And then we just need to do the numbering. So we could have it as 3, or if we count from this side, it will also be 3. So this is the same either way. So this will be 3-hexene. Now there are also some parts unaccounted for. So we've accounted for the longest carbon chain, but that means that these little extra parts are not accounted for. So we need to include them in our molecule. So again, it won't matter which way we count from, but we'll do the blue counting. So if we count from the blue, we see on the 3rd carbon, we have a 1 carbon chain, okay? And 1, Mary, methyl. So we have a methyl group on the 3rd carbon. So we say 3. So we've got 3 methyl. So 3, if it was just that, we'd have 3 methyl, 3 hexene. And then, but we also have another one on the 5th carbon. So this would actually become, it gets a little bit complicated, but it'll be 3,5 dimethyl 3-hexene. And that just means, so you've got 3 and 5, 2 methyl groups, and then the 3 tells you where the hexene is. So that's how you can kind of break those down to hopefully something a little bit simpler. But because it's multiple choice, you will be able to, I promise you will be able to distinguish these things. If you had it as 3 methyl, 5 methyl, 3 hexene, then you didn't do that dimethyl thing, you're still going to get the right answer because you'll be able to figure out which one it corresponds to. And this last example that we'll go through, so again, we find the functional group and we can see that common backbone that we have here. So that's our R group that way. So we have that, and then the additional part is a carboxylic acid. So this is, so that suffix is anoic acid. And then we need to count the longest carbon chain. So 1, 2, 3. Now I've done this the wrong way, so we need to go this way. So 1, 2, 3. So that makes it Mary eats plums, so propanoic acid. Oops. Propanoic acid, and then on the 2nd carbon, so here we have a methyl group. So that will be 2-methyl propanoic acid, and it's just normal propanoic acid because the functional group is on the 1st carbon. Okay, so why have I been teaching you guys all of this? Well, it comes down to the way that the organic chemistry reaction questions are in the GAMSAT. So you'll have these really, I've kind of simplified this a little bit, but you'll have these molecules that react and then they form another molecule. And what you will be given is either the name of a compound or the drawing of a compound. And that will either be what is made, or it could be what goes in. It really changes, but you're going to be given one of these. And from that information, you need to determine what the other thing is. So either what the product is or what made that product. So that's why it's very important that you can go from either a diagram into words, or from a word, or from words into a diagram, so that you can map out what's going to happen. So in all of these things, you're going to have what I like to think of as a non-variable region. So that's all the bits that I've highlighted in yellow here. They will always be fixed, but you'll have all these extra parts attached to those non-variable regions, which are R groups. So they're just hydrocarbon chains, and they can vary. So what I said about R groups before is that they can be any length. So it will give you the name of a compound, and then you need to go from the name of that compound into what do those R groups represent. So let's say we take this first example here. So this molecule here, it might say you have propanoic acid with, and it will give you the name of this compound, so you'll need to know what that is as well. What will it make? What will be the product? So you need to go from propanoic acid and determine what R and this R prime, and R prime just means a different hydrocarbon, but you need to go from this word into what it means. So if you draw this out, propanoic acid, that's a carboxylic acid. So I'll just do this quickly, but what this would be is CH2. So to make that has to be what that's the only way that you can make propanoic acid. And then what the key is you just take the non-variable region. I like to just think of it as a block, and then that will tell you what these variable regions are. And then what you need to do is then map that to the product. So you know that this hydrogen will go here, and then this green group will go here. So then you need to take those groups, redraw them in the product, and then name that compound. So you're kind of going from name to drawing to drawing to name. And it could be any combination of those, but I hope this kind of illustrates why it's so important that you can name and draw compounds. Okay, so to finish off this video, what I've done is just find a random organic reaction on the internet, and hopefully you can see that this is something that could be in the GAMSAT. So you've got some information up here that is generally quite useless, just describing the reaction. And then you have your reactant, you'll have a number of steps, and then you'll have your product at the end. And my recommendation is all you need is just to determine, all you need to do is be going from products to reactants, or reactants to products, vice versa. So just ignore all those steps, they're not relevant, and just think what is going to be the effect of, or if I have whatever molecule, what is that going to look like here? So they might give you the name of the reactant, for example, and from that name you work out that R1 is, let's say, a 2-carbon molecule, and R is a 3-carbon molecule. So you've interpreted the name, you've then drawn out this molecule, and then what you need to do is take those groups and just substitute them in. So this is R1, so that's going to go here, and this is just the plain R group, so that's going to go here and here. So I'm not going to do that because it's going to end up a very complicated molecule, but hopefully that demonstrates what you're going to do. So you've identified what those R groups are, and you're just substituting them in. So this will become a 2-carbon molecule, and these down the bottom will become 3-carbon molecules. So God knows how you'd name that. It looks very complicated and very scary, but that is far more complicated than what you'll see in the GAMSAT. They're going to be constrained to those things I talked about. So aldehydes, ketones, esters, carboxylic acids, those kind of things. So if you can get a really good handle on all those functional groups, it'll set you up really well to do those organic chemistry reaction questions. So I hope that was helpful. I know I mentioned it at the start, but if you could like, comment, and subscribe on the video, I'd really appreciate it. And hopefully this video helps you out in how you approach organic chemistry questions.